The year is 1880. The desert wind carries sand across the Giza Plateau, the same wind that has blown for 47 centuries. British archaeologist Sir Flinders Petrie stands before the Great Pyramid with instruments of brass and steel, tools representing the pinnacle of Victorian precision engineering. He has come to measure, to quantify, to understand. What he discovers in the months that follow will haunt him for the rest of his life. The measurements he records, painstakingly, obsessively, with instruments accurate to 1/100th of an inch, reveal something that should not be possible. The Great Pyramid, supposedly built by Bronze Age workers with copper tools and stone hammers, displays a level of precision that surpasses most modern construction. The base is level to within less than an inch across its 756-foot length. The sides are aligned to true north with an error of only 3/60th of a single degree. Petrie writes in his journal, his hand trembling slightly. The accuracy is such that the finest opticians in Europe could not do better. But how? How does a civilization without lasers, without computers, without even iron tools, achieve accuracy that challenges our modern capabilities? How do they move and position stones weighing 70 tons with tolerances measured in fractions of millimeters? This is not ancient history. This is an impossibility we live with every day, a monument that stands in defiance of everything we think we know about human development, technological progression, and the capabilities of the ancient world. Tonight, we embark on a journey into precision, into the razor's edge between possible and impossible. We will stand where Petrie stood, measure what he measured, and confront a truth that archaeology has struggled to explain for over 2 centuries. The Great Pyramid is not simply old. It is not simply large. It is perfect in ways that it should not be. And that perfection whispers of knowledge we have forgotten, technologies we have lost, and a vision of the ancient world that shatters our comfortable assumptions about linear human progress. There are monuments and there are mysteries. The Great Pyramid of Giza is both. A mathematical poem written in 6 million tons of stone. A testament to a level of knowledge that appears, quite literally, out of time. For 200 years, archaeologists, engineers, and mathematicians have measured its dimensions, traced its alignments, and studied its construction techniques. And for 200 years, a single question has echoed through the corridors of academic debate. How? Not how in the general sense of workforce and logistics, though those questions persist, but how in the specific, unforgiving language of precision. How do you achieve astronomical alignment accurate to arc minutes? How do you level a 13-acre base to within centimetres? How do you cut and fit stones so precisely that a razor blade cannot slip between them? These are not rhetorical questions. They are engineering problems that would challenge modern construction teams with laser levels, computer-aided design, and hydraulic machinery. Yet somehow, in an era we're told possessed only the most rudimentary tools, these problems were not just solved, they were transcended. The Great Pyramid's precision is not an interesting detail. It is the central mystery. It is the crack in our understanding of history. The anomaly that refuses to fit within the neat progression from primitive to advanced, from crude to sophisticated. And as we shall see, this precision is not random. It is not decorative. It is functional, purposeful, and woven into the very fabric of the structure with an intentionality that suggests not just skill, but knowledge. Profound, sophisticated, comprehensive knowledge of mathematics, astronomy, geodesy, and engineering principles that our textbooks insist were not yet discovered. So tonight, we measure, we calculate, we compare, and we confront the possibility that the story we've been told about human history, about the steady, linear march from ignorance to understanding, may be incomplete. That there may have been, in the deep past of our species, a wellspring of knowledge as profound as any we possess today. The precision of the Great Pyramid is not a mystery we can afford to ignore. It is evidence, hard, measurable, undeniable evidence, and evidence demands explanation. The wind still blows across Giza. The monument still stands, its perfect angles casting shadows that mark the passage of time with astronomical accuracy. And somewhere in those measurements, in those impossible tolerances and uncanny alignments, lies a truth about who we were, what we knew, and what we may have forgotten in the long centuries of human history. Are you ready to measure the impossible? To stand at the intersection of ancient achievement and modern confusion? To ask not just how the Great Pyramid was built, but what its precision tells us about the consciousness, the knowledge, and the capabilities of those who built it. Then let us begin. Let us step back 47 centuries to a time when human beings, our ancestors, people with the same brains and the same potential we possess today, created something so precise, so mathematically elegant, so astronomically aligned, that it continues to challenge our understanding of what was possible in the ancient world. The measurements await, the mystery beckons, and the precision of the ages calls us to witness what should not exist. The history of measuring the Great Pyramid is the history of disbelief. It begins not with Flinders Petrie, but centuries earlier with Arab scholars in the medieval period who first attempted to quantify the monument's dimensions. Al-Ma'mun, the Abbasid Caliph, forces entry into the pyramid in 820 AD, searching for treasure and ancient knowledge. His surveyors record dimensions that seem exaggerated, impossibly precise for something built millennia before. European scholars dismiss these early measurements as fantasy. Ancient peoples, they reason, did not possess the mathematical sophistication for such precision. The measurements must be errors, exaggerations, or fabrications. But then comes Napoleon. In 1798, Napoleon Bonaparte arrives in Egypt with not just an army, but a contingent of scholars, scientists, and engineers, 167 of the finest minds in France. They are there to measure, to map, to quantify Egypt's monuments with Enlightenment precision. The team includes mathematicians, astronomers, and surveyors equipped with the finest instruments Europe can produce. They measure the Great Pyramid, and their findings confirm what the medieval scholars had recorded. The precision is real. The base forms an almost perfect square, each side approximately 230 metres long, with variations of less than 2 centimetres. In a structure whose perimeter spans nearly a kilometre, the error is negligible, less than 0.01%. The angles at each corner measure 90 degrees with deviations so slight they fall within the measurement error of the instruments themselves. But it is the alignment that stuns Napoleon's astronomers. The pyramid sides face the cardinal directions, north, south, east, west, with breathtaking accuracy. The northern face deviates from true north by less than 4 arc minutes. To put this in perspective, the human eye cannot perceive such a deviation without instruments. The French scholars return to Paris with their measurements. They publish their findings in the monumental Description de l'Égypte, 23 volumes documenting Egypt's monuments. The data is precise, carefully recorded, scientifically verified, and it raises more questions than it answers. How did Bronze Age engineers achieve such astronomical alignment? The compass had not been invented. The North Star, Polaris, was not the pole star in 2560 BC due to the precession of Earth's axis. So how? What method, what technique, what understanding of celestial mechanics allowed such precision? The academic world begins to fracture over these questions. Some scholars propose lost instruments, sophisticated tools that left no archaeological trace. Others suggest methods involving star sightings and geometric calculations, methods that would require mathematical knowledge supposedly not yet formalized in ancient Egypt. A few, more controversially, begin to whisper of lost knowledge, of civilizations before recorded history, of technological sophistication that did not fit within the comfortable narrative of human progress from primitive to advanced. But Napoleon's expedition is just the beginning. The real confrontation with impossible precision comes 80 years later, when Flinders Petrie arrives in Egypt with a different goal, not to confirm the measurements, but to disprove them. Flinders Petrie is 27 years old when he reaches Giza in 1880. He is not yet the legend he will become, the father of modern archaeology, the man who will revolutionize excavation techniques and establish the systematic study of ancient Egypt. He is simply a young surveyor with excellent instruments and a mission: to prove that the Great Pyramid is not as precise as people claim. His father, an engineer, believes the pyramid encodes mystical proportions and divine measurements. Young Petrie, trained in rigorous scientific methodology, intends to measure the structure so precisely that such romantic notions will be dispelled by hard data. He lives in a tomb for 2 years. He works primarily at night, when the desert heat does not expand the stones and distort measurements. He uses custom-made instruments, theodolites, and measuring rods designed to tolerances far exceeding standard surveying equipment. He measures every surface he can access, every angle, every alignment. And slowly, measurement by measurement, his skepticism transforms into awe. The base of the pyramid is not just level, it is level beyond what should be achievable with ancient technology. The foundation stones, each weighing several tons, are positioned so precisely that the entire base plane varies by less than 2.1 centimetres across its 13-acre expanse. This is not approximate. This is not good enough. This is a level of precision that modern contractors, with laser levels and computer-assisted grading, would be proud to achieve. But how was it achieved? Petrie examines the site, searching for evidence of levelling techniques. He finds channels carved into bedrock, suggesting water was used as a level, a known ancient technique. But even with water levelling, achieving such precision across such an area would require extraordinary care, mathematical understanding of error propagation, and a commitment to perfection that seems incongruous with our image of Bronze Age construction. The casing stones, the smooth limestone that once covered the pyramid's exterior, present an even greater puzzle. Most have been removed over the centuries, repurposed for buildings in Cairo. But Petrie finds some still in place at the base, and what he measures makes his hands shake. The casing stones are dressed so finely that the joints between them are virtually invisible. He attempts to insert a razor blade between stones and cannot. The gaps are measured in hundredths of an inch over surfaces spanning several feet. The stones fit together with a precision that exceeds most modern masonry. But it's not just that they fit closely. They fit at precise angles. Each casing stone is cut to contribute to the pyramid's overall slope of approximately 51 degrees, 51 minutes. A specific angle that, as Petrie will later realize, may encode the mathematical ratio of pi and phi, the golden ratio. Every stone cut to precise angles. Every stone fitted with invisible joints, thousands of them, covering 13 acres of surface area, rising to a height of 481 feet. How? With what tools? With what measurements? With what understanding of geometry and structural engineering? Petrie measures the internal passages. The descending passage, boring into the bedrock at a precise angle of 26 degrees, 31 minutes, 23 seconds. Not approximately that angle. Exactly that angle, maintained over a length of more than 100 metres. The passage is so straight, so true, that when measured with a theodolite, the deviation from perfect alignment is negligible. Drilling such a passage, maintaining such an angle through solid limestone and bedrock, would be challenging with modern tunnelling equipment. Yet the ancient Egyptians somehow achieved it with, we are told, copper tools and stone hammers. Petrie examines the walls of the passage, searching for tool marks that might explain the technique. What he finds is puzzling. The surfaces are smooth, almost polished. There are no chisel marks, no obvious signs of pecking or hammering. The rock appears to have been cut with something, but with what? In the king's chamber, Petrie encounters another impossibility. The chamber is constructed from massive granite blocks, some weighing as much as 70 tons. The blocks are fitted together with extraordinary precision. But more remarkable is the chamber itself. It is a perfect rectangle, its dimensions maintaining precise ratios. The length is exactly twice the width. The ceiling height creates a double cube in section. But perfection in rooms is not uncommon. What stuns Petrie is the precision of the granite itself. When he measures the interior surfaces with his instruments, he finds they are flat to within tolerances of a few thousandths of an inch. The corners are square to the same tolerance. This is precision engineering. This is not rough construction or approximate measurements. This is the work of people who understood exactitude, who possessed tools and techniques capable of achieving it, and who cared enough to make it perfect. Petrie's journal entries grow increasingly perplexed. He writes of workmanship of the utmost care and precision. He notes that the accuracy of the work is such that nothing can be more skillful. He confesses that the precision is a marvel, seeing that it could be exceeded only by instruments of the greatest refinement. But Petrie is a scientist. He records what he measures. He does not speculate wildly. He does not propose impossible technologies or lost civilizations. He simply documents the data that speaks of capabilities that should not exist in the 3rd millennium BC. His measurements are published in 1883 in The Pyramids and Temples of Giza. The book becomes the foundation of modern pyramid research, the baseline against which all subsequent measurements are compared. And it stands as a challenge. Here is the data. Here is the precision. Now explain it. The traditional narrative of pyramid construction is well established. We're told that the ancient Egyptians built the Great Pyramid during the reign of Pharaoh Khufu, around 2560 BC, using the tools and techniques available in that era. Copper tools, stone hammers, wooden sledges, and immense quantities of human labour. Copper tools. This is crucial. Ancient Egypt was in the late Copper Age, just transitioning to bronze. The hardest tools available were copper chisels and saws. Copper is soft, softer than many stones used in pyramid construction. The idea that copper tools were used to cut and shape 6 million tons of limestone and granite blocks has been accepted for centuries, based on archaeological evidence of copper tools found in ancient sites. But when engineers examine the precision of the Great Pyramid with knowledge of materials science and metalworking, a problem emerges. A significant problem. Limestone can be worked with copper tools, though the copper dulls quickly and must be constantly resharpened. Experimental archaeology has demonstrated this. Teams have attempted to cut limestone blocks using replica copper tools and ancient techniques. It is possible, but slow, laborious, and imprecise. Achieving smooth surfaces requires extensive grinding and polishing. Yet Petrie's measurements show surfaces finished to tolerances of thousandths of an inch. This level of precision is not typically achievable through the abrasive, imprecise process of copper tool work. It suggests some form of fine finishing technique, but what? And then there is granite. Granite is significantly harder than copper. On the Mohs hardness scale, copper measures around 3, while granite, composed of quartz, feldspar, and mica, measures 6 to 7. In practical terms, copper cannot cut granite. It will not hold an edge against the harder stone. Any attempt to saw or chisel granite with copper will result in the copper deforming before the granite yields. Yet the Great Pyramid contains massive granite elements, the King's Chamber, the Grand Gallery, the enormous granite plugs that block passages, and the granite sarcophagus. These elements are not roughly hewn. They are precisely cut, finished, and fitted. The sarcophagus in the King's Chamber is particularly problematic. It is carved from a single piece of red granite. The interior is hollowed out to precise dimensions, the walls uniform in thickness. The corners are sharp, clean, 90-degree angles. The surfaces are smooth, finished. Engineers who examine the sarcophagus note features that suggest machine tooling. Regular, parallel striations inside the hollowed interior, consistent wall thickness, and precision that exceeds what hand tools typically achieve. The tolerances are such that when measured with modern instruments, the variations are minimal, far less than would be expected from hand chiselling. Christopher Dunn, a precision engineer who has studied the pyramid for decades, measures core samples from the pyramid stone. He finds something remarkable: evidence of tubular drilling, holes drilled into granite using hollow tubes, showing a spiral pattern that indicates the drill descended through the hard stone at a rate that seems impossible with copper tools. Dunn calculates that the drill marks suggest a descent rate of approximately 1 inch per revolution. To achieve this in granite with copper tools would require enormous force and pressure. He estimates it would require at least 2 tons of force, far beyond what human operators could apply manually. What kind of drill system could achieve such penetration rates? Dunn proposes that the ancient Egyptians must have possessed a drilling technology far more sophisticated than simple copper tools, perhaps involving advanced drill bits, efficient power transmission, and even the use of harder abrasives or cutting surfaces. But where is the evidence for such technology? Where are the advanced drills, the powered systems, the sophisticated tool-making workshops? The archaeological record shows copper tools, stone hammers, wooden implements. There are no artefacts suggesting the level of technological sophistication Dunn's analysis implies. This is the paradox. The precision exists, measurable and undeniable. The traditional tools exist, found in archaeological contexts. But the two don't reconcile. The tools cannot produce the precision. The precision should not exist with only those tools available. So what's missing? What technique, what knowledge, what technological element has left no trace in the archaeological record, but must have existed to explain what we can measure? Some researchers propose that the ancient Egyptians possessed knowledge of harder abrasives, perhaps incorporating sand or corundum into their cutting processes to enhance the effectiveness of copper tools. This is plausible and supported by some experimental archaeology. But even with abrasives, achieving the precision measured by Petrie seems to require not just hard materials, but sophisticated techniques, methods for maintaining alignment, for measuring accuracy, for quality control. Others suggest that we underestimate the skill and patience of ancient craftsmen, that with enough time, careful technique, and attention to detail, a skilled worker with simple tools can achieve remarkable precision. This too has merit. Human capability, when honed through years of training and practice, can transcend our expectations. But there's a limit to this argument. Precision engineering is not just about skill, it's about measurement. To achieve precision, you must be able to measure it. You must have instruments that can verify accuracy, detect deviations, and guide corrections. What instruments did the ancient Egyptians possess? The archaeological record shows plumb bobs, levelling squares, measuring rods. Simple tools, functional but limited in their precision. Did they possess more sophisticated measuring instruments that have not survived? Instruments made of materials that deteriorated over millennia? Or did they possess knowledge, mathematical and geometric knowledge, that allowed them to achieve precision through calculation and technique rather than instrumentation? This question brings us to the mathematical heart of the Great Pyramid. Numbers do not lie, they do not exaggerate, they do not embellish. And in the dimensions of the Great Pyramid, numbers whisper of a mathematical sophistication that should not exist in 2560 BC. Let's begin with the most famous ratio, pi. Pi, the ratio of a circle's circumference to its diameter, is approximately 3.14 to 159. We learn it in school. we use it in calculations involving circles and spheres. It is a fundamental mathematical constant, irrational and infinite in its decimal representation. The ancient Greeks are typically credited with the first rigorous mathematical investigation of pi. Archimedes, in the 3rd century BC, calculated pi to a precision that would not be surpassed for centuries. Before that, Babylonian and Egyptian mathematicians had approximations, useful for practical calculations, but not precise. The Rhind mathematical papyrus, an ancient Egyptian text from around 1650 BC, gives a value for pi of approximately 3.16. Close, but not exact. This papyrus is one of our primary sources for understanding ancient Egyptian mathematics. It shows practical problem-solving, geometry used for surveying and construction, but not advanced theoretical mathematics. Yet when we measure the Great Pyramid, pi appears with uncanny precision. The height of the pyramid, as originally constructed, including the capstone now missing, was approximately 280 Egyptian royal cubits. The perimeter of the base was approximately 760 royal cubits. If you divide the perimeter by twice the height, 560, you get 3.142857, remarkably close to pi. This could be coincidence. Ratios can align by chance, but the precision is suspicious. The slope angle of the pyramid, 51 degrees 51 minutes, is the angle you get when you use the ratio of pi to create a relationship between height and base. Specifically, if you design a pyramid where the apothegm, the slant height from base to apex, divided by half the base length equals the square root of phi, the golden ratio approximately 1.618. You automatically encode pi in the structure's overall proportions. This is not simple geometry. This is sophisticated mathematical understanding, the kind that relates different constants and ratios in elegant ways. And then there's the golden ratio itself, phi. The golden ratio is another irrational number, approximately 1.618. It appears throughout nature, in the spiral of nautilus shells, the arrangement of seeds in sunflowers, the proportions of the human body. Renaissance artists and architects consciously use phi to create aesthetically pleasing proportions. But the mathematical formalization of the golden ratio is typically attributed to Euclid in the 3rd century BC, and its widespread architectural use came much later. Yet in the Great Pyramid, phi appears multiple times. The ratio of the slant height to half the base is close to phi. The ratio of the height to half the base approximates the square root of phi. The triangular face of the pyramid, if analysed geometrically, embeds phi in its proportions. Again, this could be coincidence, or it could be design, intentional incorporation of mathematical ratios known and understood by the pyramid's architects. But pi and phi are just the beginning. The Great Pyramid's dimensions encode other mathematical relationships that seem too precise to be accidental. The base perimeter of 1760 cubits is almost exactly 1/2 a minute of latitude at the equator, 43,200 feet, a number that also relates to precession cycles and ancient timekeeping systems. The height-to-base ratio relates to Earth's radius and circumference in ways that suggest geodetic knowledge, understanding of Earth's dimensions. The mathematician John Taylor, in the 19th century, proposed that the pyramid was designed as a representation of Earth's northern hemisphere at a scale of 1/43,200. The height represents the radius from center to pole. The perimeter represents the equatorial circumference. When you run the numbers, the ratios work. The pyramid's dimensions do mirror Earth's proportions at that specific scale. Skeptics dismiss this as numerology, cherry-picking ratios to fit desired conclusions. And there's validity to that skepticism. With enough numbers to work with, you can find patterns in almost anything. The human mind seeks order and connection. But the precision of the construction adds weight to the mathematical arguments. If the pyramid's dimensions were approximate, if the construction was rough or imprecise, then mathematical ratios would be meaningless, mere artifacts of selective interpretation. But because the construction is precise, because the measurements are accurate to fractions of percents, the mathematical relationships take on greater significance. They suggest intentionality. They suggest that the pyramid was designed, from its inception, to encode specific mathematical knowledge. Not approximately, not symbolically, but precisely, built to exact specifications that embed pi, phi, Earth dimensions, and perhaps other constants we have yet to fully understand. And this raises the central question: how did Bronze Age architects possess such mathematical knowledge? The formal mathematics we associate with these constants would not be developed for thousands of years. The Greeks, the Islamic mathematicians, the Renaissance scholars, they are credited with advancing humanity's mathematical understanding. Yet here, in 2560 BC, stands a structure that suggests this knowledge already existed. That somewhere in the ancient world, mathematicians and architects understood pi, understood phi, understood geodesy and geometry at levels that would not be rediscovered until much later in human history. Was this knowledge indigenous to Egypt, developed through centuries of mathematical exploration by scribes and priests? The Egyptian mathematical papyri we possess show practical arithmetic, but not the kind of advanced theoretical mathematics that would be required to intentionally encode these ratios. Or did this knowledge come from elsewhere? From an earlier time, an earlier culture, a wellspring of ancient wisdom that was inherited rather than invented? The precision of the Great Pyramid does not just challenge our understanding of ancient construction capabilities. It challenges our entire narrative of mathematical development, of the progression of human knowledge from primitive counting to advanced calculus. Because the numbers in the stone suggest that someone, 47 centuries ago, understood the universe in mathematical terms as sophisticated as our own. On a clear night in Giza, if you stand at the northern face of the Great Pyramid and look up at the stars, you are looking along one of the most precise astronomical alignments on Earth. The pyramid is oriented to the cardinal directions with stunning accuracy. The mean deviation from true north is 3 arc-minutes, 3/60th of a degree. To put this in perspective, if you took a protractor and tried to measure a 3 arc-minute deviation, you would need magnification to see it. The human eye cannot detect such a small angular difference without instruments. For over 2 centuries, researchers have marvelled at this alignment and puzzled over how it was achieved. The question is deceptively simple. How do you find true north in 2560 BC? True north is not the same as magnetic north. Magnetic north, indicated by compasses, varies over time and location due to changes in Earth's magnetic field. True north is the direction toward Earth's geographic North Pole, the axis around which the planet rotates. The most common method for finding true north, both in ancient and modern times, involves celestial observation. You watch the stars. But which stars and how do you use them? The pole star, Polaris, in our current era, seems like an obvious answer. Polaris sits almost directly above Earth's North Pole, appearing stationary while other stars rotate around it. If you can identify Polaris, you've found north. But here's the problem. Polaris was not the pole star in 2560 BC. Earth's rotational axis precesses, wobbles, in a slow cycle taking approximately 26,000 years to complete. This precession changes which star, if any, sits near the celestial pole. In 2560 BC, Polaris was more than 20 degrees away from the pole. There was no bright star marking true north, so how did the pyramid builders find it? One theory involves simultaneous transits, observing 2 stars at specific moments when they align vertically, one above the other, in the northern sky. By measuring the exact center point between their positions, you can calculate celestial north, but this requires precise timing, careful observation, and mathematical calculation. It's possible, but complex, not the kind of technique you'd expect from a civilization we characterize as primitive. Another theory proposes the shadow square method, using the sun's shadow cast by a vertical rod to track its movement throughout the day. True north lies perpendicular to the line connecting the shadow's eastern and western extremes. This method is simpler but requires precision in marking and measuring shadow positions. Experimental archaeologists have attempted both techniques using replica ancient instruments. With practice and care, they can achieve alignments within a degree or two of true north. Impressive, but not the 3 arc-minute precision of the Great Pyramid. So how? What technique, what refinement, what understanding allowed such extraordinary accuracy? Kate Spence, an Egyptologist at Cambridge, proposed an elegant solution in 2000. She theorized that the builders used 2 specific stars, Kochab in Ursa Minor and Mizar in Ursa Major, which in 2467 BC, close to the pyramid's construction date, would have aligned vertically in a way that marked true north. This alignment occurred due to precession and was a unique temporal event. Before and after that specific period, these stars would not align correctly. If Spence is correct, it explains both the precision and the slight deviation. The pyramid's alignment isn't perfect to our current north because it was aligned to where true north appeared in the sky using a technique that was nearly perfect for its time. But precession has since shifted the reference point. But even if we accept this explanation, questions remain. Kochab and Mizar are faint stars. Observing their precise alignment would require dark skies, patient observation, and sophisticated understanding of celestial mechanics. The builders would need to know that this particular alignment indicated true north, which requires theoretical knowledge of precession, stellar motion, and geometric principles. And the pyramid is not the only structure at Giza aligned with such precision. The second pyramid, Khafres, and the third pyramid, Menkores, are similarly aligned, all oriented within arc-minutes of the cardinal directions. This consistency suggests not a one-time lucky measurement, but a standardized technique, a method passed down and repeatedly employed with success. The alignment extends beyond orientation. The internal passages of the Great Pyramid are also astronomically significant. The descending passage, cutting down into the bedrock at a 26-degree angle, once pointed, when the pyramid was new, toward the star Thuban, the pole star of ancient Egypt. Thuban was the closest bright star to the celestial pole in 2560 BC, though still several degrees away. The passage's alignment is so precise that for a few minutes each night, Thuban's light would shine directly down the passage, a celestial event that could be observed from deep within the pyramid's interior. Was this intentional? Did the builders design the passage to frame the pole star, creating a connection between the earthly structure and the heavens? The ascending passage and grand gallery ascended approximately 26 degrees as well, the same angle maintained with precision through hundreds of feet of limestone. Some researchers note that this angle corresponds to specific stellar alignments, particularly with stars in Orion's belt, which held profound religious significance for the ancient Egyptians. Robert Bauval, in his controversial but intriguing Orion correlation theory, proposed that the 3 pyramids of Giza are positioned and sized to mirror the 3 stars of Orion's belt. When you map the pyramid's positions and compare them to the stars' positions, accounting for precession, there's a correlation, though scholars debate how significant and intentional it may be. Whether or not Bauval's specific theory holds, the broader point stands. The Great Pyramid is not just aligned to Earth's cardinal directions. It is aligned to the cosmos. It is a terrestrial structure designed to reflect and connect with celestial patterns. This astronomical precision reveals something profound about the pyramid builders' worldview. They did not see the pyramid as merely a tomb or a monument to royal power. They saw it as a cosmic instrument, a structure that bound Earth to heaven, that reflected the order of the stars in stone, that served as a bridge between human and divine realms. But creating such a structure requires more than religious vision. It requires astronomical knowledge, precise, technical, quantifiable knowledge. It requires the ability to track stellar positions over time, to understand precession, to calculate angles and alignments with accuracy that borders on the modern. Where did this knowledge come from? How was it developed? The ancient Egyptians certainly observed the sky. All agricultural civilizations do, tracking seasons and planning harvests by stellar and solar cycles. Egyptian priests were known to be keen astronomers, recording observations over generations. But there's a difference between observational astronomy, tracking when specific stars rise or set, and theoretical astronomy, which requires understanding Earth's rotation, the celestial sphere's geometry, and the mathematical relationships between angles, positions, and time. The precision of the pyramid suggests theoretical knowledge. It suggests that someone understood not just that stars move, but why they move, how their positions change over time, and how to use that knowledge to create permanent alignments in stone. And here we encounter the same pattern we've seen with the construction precision and mathematical encoding. Evidence of knowledge that seems too advanced, too sophisticated for its time. Knowledge that should not exist, yet clearly does, written in the alignment of 6 million tons of stone. Precision in orientation and dimension is impressive, but precision in stonework, in the cutting, shaping and fitting of individual blocks, is where the Great Pyramid transcends the possible and enters the realm of the impossible. Let us talk about the casing stones. Originally, the entire pyramid was covered in approximately 144,000 smooth, white limestone casing stones. Each stone weighed several tons. Together, they formed a smooth, continuous surface that caught sunlight and made the pyramid gleam like a mirror. Ancient sources describe it as blindingly bright, visible from miles away. Most of these casing stones were removed centuries ago, stripped away to build Cairo's mosques and palaces. But some remain at the pyramid's base, and those that remain tell a story that conventional archaeology struggles to explain. The casing stones are fitted together with joints so fine that you cannot insert a blade between them. Not a knife blade, too thick. Not a razor blade, still too thick. The gaps are measured in thousandths of an inch, often imperceptible to the naked eye. But it's not just that the stones fit closely, they fit at precise angles. Each stone contributes to the pyramid's overall slope, cut to exact specifications that ensure the structure tapers uniformly from base to apex. Each stone interfaces with 4 neighbours, above, below, left, right, and all interfaces must be correct for the entire surface to be smooth and continuous. Imagine the complexity. You have 144,000 stones, each weighing 2.5 tons, each cut to unique dimensions, because each occupies a different position on the pyramid's sloping surface. Each must fit perfectly with its neighbours, edges aligned, angles correct, gaps minimal. How do you plan such a project? How do you calculate the dimensions for each stone? How do you ensure that stone number 52,438, cut by one team of workers, will precisely fit next to stone 52,437, cut by another team, perhaps months apart? This requires more than skill. It requires system, a comprehensive system of measurement, calculation, and quality control that ensures consistency across thousands of individual elements. Modern construction achieves this through engineering drawings, computer-aided design, precise measurements, and standardized tolerances. But what system did the ancient Egyptians use? And even if we grant that they had such a system, plans, measurements, organizational structure, we still face the practical question: how were the stones cut and shaped to such precision? The casing stones are limestone, quarried from Tura on the east bank of the Nile. Tura limestone is fine-grained and relatively soft, easier to work than granite. In theory, copper tools and abrasives could shape it. But achieving the precision seen in the casing stones requires more than crude chiselling. The surfaces must be flat, not approximately flat, but truly planar within fractions of a millimetre. Edges must be straight. Angles must be exact. How do you verify these qualities in the field with ancient tools? Modern stonemasonry uses straight edges, levels, squares and gauges to check work constantly. Ancient Egyptians certainly had similar tools. Straight edges have been found in archaeological contexts, as have plumb bobs and right-angle squares. But the precision of the casing stones exceeds what simple hand tools typically achieve. It suggests either extraordinary skill, craftsmen working at the highest levels of their art, spending weeks or months on each stone, or some form of advanced technique, some method of shaping and finishing that left surfaces accurate to modern standards. And then there's the question of the joints themselves. The casing stones are not stacked with simple, horizontal joints. Many are fitted together with interlocking joints, geometric interfaces that lock stones together like three-dimensional puzzles. Some stones have angled faces that dovetail with their neighbours, creating mechanical bonds that strengthen the structure and resist displacement. Creating such joints requires three-dimensional thinking. You must visualize how stones interact in space, how shapes fit together, how geometry creates strength. This is sophisticated masonry, the kind that emerges from deep understanding of structural principles and material behaviour. But perhaps most puzzling is the mortar. There is mortar between the casing stones, thin layers, nearly invisible due to the tightness of the joints. Chemical analysis of this mortar reveals that it is stronger than the limestone blocks themselves. It's a gypsum-based mortar, precisely mixed, containing additives that enhance bonding. Why? If the stones fit so precisely, why use mortar at all? The common explanation is that mortar served as lubrication, helping stones slide into position during installation. But if this were the only purpose, the mortar need not be so precisely formulated or so strong. Perhaps the mortar serves structural purposes, distributing loads and preventing stress concentrations. Or perhaps it has properties we don't fully understand, ancient concrete formulations that have been lost to time. Now let's move inside the pyramid, to the granite elements. Granite is vastly harder than limestone. It is an igneous rock, crystalline and dense, containing quartz, one of the hardest common minerals. Working granite is exponentially more difficult than working limestone. Yet the Great Pyramid contains massive granite elements, the king's chamber walls and ceiling, the granite beams above the chamber, weighing up to 70 tons each, granite plugs blocking internal passages, and the enigmatic granite sarcophagus. The king's chamber is constructed from enormous Aswan granite blocks. The walls are smooth, the corners are sharp and square, the ceiling is perfectly level. The chamber's acoustic properties are remarkable. It resonates at specific frequencies when sounds are produced inside it, suggesting that the dimensions were chosen with acoustic design in mind. But how were these massive granite blocks shaped? Aswan granite contains feldspar, quartz, and mica. Copper tools will not cut it effectively. Pounding with dolerite hammers, another proposed ancient technique, is possible but slow and imprecise. It produces rough surfaces, not the smooth finishes seen in the king's chamber. Christopher Dunn, the precision engineer, has measured the surfaces inside the king's chamber with modern instruments. He finds flatness tolerances of 0.01 inches across surfaces several feet long. In manufacturing terms, this is precision flat, the kind of surface quality used in metrology and machine tooling. How? What method creates such surfaces in granite? Dunn has proposed machine tooling, not necessarily modern machines, but advanced mechanical devices employing principles of power transmission, precision guidance, and effective cutting techniques. He points to marks on the stone, parallel striations, uniform depths, consistent spacing, characteristics suggestive of mechanized cutting rather than handwork. The academic response to Dunn's proposals is typically dismissive. Mainstream archaeology insists that ancient Egyptians used the tools we find in the archaeological record: copper, dolerite, sand abrasives. Any precision achieved was through skill, patience, and labour. Lots of labour. But Dunn and others ask a simple question. If you give a skilled craftsman copper tools and dolerite hammers, can they replicate what we see in the Great Pyramid? Not approximately, not in the same general style, but precisely. Can they achieve the measured tolerances, the surface finishes, the structural precision? Experiments have been conducted. Teams have attempted to cut and shape granite using replica ancient tools. The results are mixed. Yes, granite can be worked with dolerite hammers and copper saws enhanced with quartz sand. But the process is extremely slow, the precision is limited, and the surface quality does not match what's seen in the pyramid. Perhaps the ancient Egyptians were simply better at it, more patient, more skilled, more committed to perfection. Perhaps there are techniques we haven't rediscovered yet, lost methods that made the work faster or more precise. Or perhaps, and this is where the conflict deepens, our understanding of ancient Egyptian technological capabilities is incomplete. Perhaps they had tools and techniques that left no obvious archaeological trace. Perhaps they understood mechanical principles, material science and engineering at levels we don't credit them with. The precision of the stones whispers this possibility. The measurements don't lie. The surfaces are flat. The joints are tight. The angles are exact. This level of precision exists. It is measurable, quantifiable, undeniable, and it challenges us to explain how it came to be. Let us turn now to a different kind of impossibility, not technical, but organizational. The traditional estimate is that the Great Pyramid took approximately 20 years to build, employing a workforce that varied from 20,000 to 100,000 workers, depending on the season and construction phase. Let's use the conservative estimate of 2.3 million stone blocks. Recent surveys suggest this number, down from earlier estimates of 2.6 million. If construction took 20 years, that's 115,000 blocks per year. Divided across 12 months, that's 9,983 blocks per month. Divided across 30 days, that's 319 blocks per day. 319 blocks per day. Every day. For 20 years. Each block averages 2.5 tonnes, though many are much larger. Each block must be quarried, shaped, transported, many from across the Nile or from quarries miles away, and then lifted into position, fitted precisely, and secured. 319 times per day. If we assume a 10-hour workday, that's one block every 2 minutes. Not one team finishing a block every 2 minutes, but the entire construction site, from quarry to installation, must complete the full cycle for one block every 2 minutes, continuously, for 2 decades. Can this be done? From a pure logistics standpoint, is such a pace achievable? Modern construction projects offer some comparison. The Hoover Dam, built in the 1930s with modern machinery, employed about 21,000 workers and took 5 years to complete. The dam required 3.25 million cubic yards of concrete, comparable in volume to the Great Pyramid. But the Hoover Dam was built with trucks, cranes, excavators, concrete mixers and conveyor systems. Electricity powered tools and lighting for around-the-clock work. Engineers had blueprints, schedules, radio communication. The Great Pyramid was built with human and animal muscle power, simple tools, and, according to conventional archaeology, no advanced lifting devices beyond ramps and levers. The logistical challenge is staggering. Consider just one aspect, the workforce itself. 20,000 to 100,000 workers need to be fed, housed, supplied with water, given tools, supervised and organised. They need bread, beer, vegetables, meat. Egyptian tomb paintings and papyrus records tell us pyramid workers were well fed, not slaves, but skilled labourers and farmers fulfilling civic duty. Feeding 20,000 workers requires vast quantities of grain. Growing that grain requires farmland, irrigation, harvest labour. Transporting that grain requires boats, storage facilities, distribution systems. Baking bread for 20,000 people daily requires bakeries, bakers, fuel for ovens. The project doesn't just build a pyramid, it sustains an entire city, a temporary settlement that must function efficiently for 2 decades. Archaeological evidence confirms this city existed. Excavations near the pyramids have uncovered workers' villages, bakeries, breweries, copper workshops, housing, and burial grounds for workers. The infrastructure was real, extensive, and well organised. But even granting that such organisation existed, we return to the technical challenge: moving and positioning stones with precision. The ramp theory is the most commonly proposed solution. A massive ramp or system of ramps spiralling around or leading up to the pyramid, allowing workers to drag stones upward using sledges and lubrication. But the numbers are problematic. As the pyramid rises, the ramp must rise with it. To reach the pyramid's apex at 481 feet, a ramp with a reasonable gradient, say 7 to 10 degrees to allow stones to be dragged upward, must extend thousands of feet. The volume of material in such a ramp would rival or exceed the pyramid itself. And as the pyramid nears completion, the ramp becomes impossibly narrow at the top, too narrow for teams of workers to manoeuvre large stones into the precisely diminishing upper courses. Some researchers propose internal ramps spiralling up within the pyramid structure itself. French architect Jean-Pierre Houdin has developed detailed models of such a system, and there's some indirect evidence, microgravimetry studies showing possible void spaces, that internal ramps may exist. But even with ramps, we face the precision problem. How do you ensure that a multi-ton block dragged up a ramp by dozens of workers lands in exactly the right position, aligned, level, fitted tightly to its neighbours? One hypothesis involves leaving stones slightly oversized, then trimming them in place after positioning. This would allow for final adjustments and tight fitting. But it complicates the logistics further. Each stone must be shaped twice, once at the quarry and once in situ. And it requires master craftsmen at every level of the pyramid, constantly checking, measuring, and finishing stones. With 319 blocks installed per day, that's a small army of skilled masons working simultaneously, each maintaining the overall precision standards. Perhaps most puzzling, there are no obvious mistakes. In any massive construction project, errors occur. Blocks don't fit correctly. Measurements are slightly off. Corrections must be made, resulting in visible irregularities or workarounds. The Great Pyramid has remarkably few such errors. Yes, there are minor variations. It is not absolutely perfect, but the overall precision is maintained throughout. From foundation to apex, the quality control is extraordinary. This suggests systems. It suggests standardization, training, oversight, and methodology. It suggests an organizational sophistication that rivals modern project management, but developed in a society we often characterize as primitive, autocratic, and dependent on brute force labor. The workforce that built the Great Pyramid was not a mob of slaves whipped into submission. It was a coordinated, skilled, organized body of workers, engineers, surveyors, masons, laborers, logistics coordinators, tool makers, and supervisors, all working within a system designed to achieve precision at scale. Such a system does not appear spontaneously. It evolves through experience, through trial and error, through accumulated knowledge passed down across generations. But the Great Pyramid is Khufu's pyramid, built supposedly early in Egypt's pyramid building tradition. Yes, there were earlier pyramids, smaller and simpler. But the leap from those to the Great Pyramid is immense, like going from building a house to building a skyscraper. Where did the knowledge come from? How was the system developed? Why is the Great Pyramid so much more precise, so much more sophisticated than the pyramids that came immediately before and after it? These questions have no comfortable answers within the conventional timeline. They suggest that either the knowledge and organizational capacity existed earlier than we recognize, developed through centuries of experimentation we haven't fully documented. The Great Pyramid represents a unique convergence of talent, resources and vision, a one-time achievement that pushed ancient Egyptian capabilities to their absolute limit. The builders inherited knowledge from an earlier source, applying techniques and understanding that did not originate in Egypt itself. The first possibility is plausible, but requires us to rethink Egyptian prehistory, to imagine a longer, more complex development of mathematical and engineering knowledge. The second possibility honours the achievement but strains credibility. How does a civilization suddenly leap to such precision, then never fully match it again? The third possibility opens doors to alternative histories, to theories of lost civilizations, ancient global connections, or knowledge transmitted through channels we don't yet understand. The evidence is the precision itself, the measurements, the alignments, the stonework, all of it, standing in defiance of easy explanations. For 200 years, the Great Pyramid has been the centre of a controversy that pits mainstream archaeology against alternative researchers, academics against engineers, conventional history against imaginative speculation. On one side, Egyptologists and archaeologists who insist that the pyramid was built by the ancient Egyptians using the tools and techniques available in the 3rd millennium BC. They point to archaeological evidence, worker villages, tool artifacts, quarry inscriptions, and historical texts, as proof that the pyramid is exactly what conventional history says it is: a tomb for Pharaoh Khufu, built through organized labor and remarkable but human engineering. On the other side, a diverse group of engineers, mathematicians, and alternative historians who argue that the pyramid's precision exceeds what Bronze Age technology could achieve. They propose various alternatives: advanced ancient civilizations, lost technologies, even extraterrestrial influence, to explain the inexplicable. The conflict is not just academic, it is deeply emotional, touching on questions of human capability, historical identity, and the progress of civilization. Mainstream archaeology's position rests on a coherent worldview. Human societies develop gradually, learning from experience, building on previous achievements. The Egyptians built the Great Pyramid because they had been building pyramids and tombs for generations, steadily improving their techniques. This view is supported by stratigraphy, the archaeological layering of sites showing progressive development. It's supported by textual evidence, inscriptions mentioning Khufu, hieroglyphic records of construction projects. It's supported by comparative evidence, other pyramids, temples, and monuments showing similar techniques and tools. But this view struggles with the precision. It explains the how in general terms: ramps, levers, many workers, but falters on the specifics. How do you achieve 3 arc-minute alignment without sophisticated instruments? How do you maintain planar surfaces within thousandths of an inch using copper chisels? The alternative researchers focus on these specifics. Christopher Dunn points to machine-like precision. Graham Hancock notes astronomical and mathematical sophistication that seems anachronistic. Robert Bauval argues for knowledge of precession that shouldn't exist yet. John Anthony West suggests water erosion on the Sphinx, indicating far greater age than conventional dating. Their arguments are often dismissed as pseudoscience, and sometimes rightly so. When they leap to conclusions without sufficient evidence, when they cherry-pick data, when they propose wildly speculative theories without rigorous methodology. But dismissing all alternative research is intellectually lazy. Some of their observations are valid. Some questions they raise are legitimate. The precision is real. The mathematical relationships are measurable. The astronomical alignments are accurate. Refusing to engage with these facts because they're uncomfortable, because they challenge established narratives, is not science. It's dogma. The healthiest approach is to hold tension, acknowledge the precision, accept that it challenges our understanding, but maintain rigorous standards of evidence and logic when proposing explanations. Perhaps the ancient Egyptians were more sophisticated than we've given them credit for. Perhaps they possessed knowledge, mathematical, astronomical, engineering, that we've underestimated because we focus on artifacts rather than intellectual achievements. Perhaps there were connections between ancient cultures we haven't fully recognized, trade routes, knowledge exchanges, movements of ideas and techniques that created pockets of advanced understanding. Perhaps some techniques, some tools, have not survived in the archaeological record because they were made of perishable materials or were rare enough that we simply haven't found them yet. The honest answer is, we don't know. We don't know how the Great Pyramid achieved its precision. We have theories, experiments, and educated guesses. But we don't know. And perhaps that's okay. Perhaps mystery is acceptable. Perhaps saying, we're not sure yet, is better than forcing the evidence to fit comfortable narratives. The conflict will not die because the precision will not disappear. The measurements will always be there, challenging each new generation of researchers to explain them. And in that challenge lies opportunity, the opportunity to ask better questions, conduct better experiments, and open our minds to possibilities we might have dismissed too quickly. After all the measurements, all the theories, all the debates, what does the precision of the Great Pyramid actually tell us? It speaks of consciousness, not primitive consciousness, not the consciousness of people barely removed from animal survival, but sophisticated consciousness, minds capable of abstract thought, mathematical reasoning, complex planning, and long-term vision. The precision is not decorative, it is not accidental, it is intentional, the product of minds that valued exactitude, that understood the importance of measurement, that possessed the intellectual tools to conceive of perfection and the technical tools to achieve it. This challenges our deepest assumptions about ancient peoples. We tend to project a narrative of progress, assuming that human intelligence, capability, and sophistication have increased over time. We imagine ancient people as less capable, their minds constrained by superstition and lack of technology. But the brain that conceived the Great Pyramid is identical to the brain reading these words. Homo sapiens in 2560 BC had the same neurological hardware we possess today, same capacity for reason, imagination, and complex thought. What they lacked was accumulated knowledge, centuries of scientific discovery, technological development, and cultural advancement that we take for granted. But raw intelligence, capacity for sophisticated thinking, that was identical. The Great Pyramid proves this. It proves that ancient minds could conceive of precision engineering, could develop mathematical relationships, could organize massive projects, could solve complex problems. They did not need computers to calculate angles. They had geometry. They did not need lasers to find true north. They had the stars. They did not need modern materials to achieve precision. They had patience, skill, and methods we're still trying to fully understand. The precision speaks of values. It says, we cared about getting this right. We didn't accept good enough. We pursued perfection. Why? What motivated such obsessive precision? Practical reasons certainly. A precisely built pyramid would be more stable, more durable. But beyond that, the precision suggests something deeper. A worldview in which order, harmony, and mathematical relationships were sacred. The ancient Egyptians believed in Ma'at, the concept of cosmic order, balance, truth, and justice. Ma'at was not just an ethical principle, it was a cosmological one. The universe was ordered, and human activity should reflect that order. Building a structure with mathematical precision, aligned to the stars, embodying geometric relationships, this was not just construction. It was an act of cosmic participation, creating on Earth a reflection of heavenly perfection. In this worldview, precision was sacred. It was a way of honoring the gods, of aligning human work with divine order. Tolerances of thousandths of an inch were not excessive. They were necessary to properly reflect the cosmic harmony the structure was meant to embody. This is sophisticated theology, sophisticated philosophy. It's a worldview that integrates mathematics, astronomy, engineering, and religion into a unified understanding of reality. And it produced the Great Pyramid, a structure that still, 47 centuries later, inspires awe precisely because of its perfection. The Great Pyramid is not an isolated anomaly. It stands within a broader pattern of ancient structures around the world that display remarkable precision, astronomical alignment, and sophisticated engineering. Stonehenge in England, built over a period from 3000 to 2000 BC, aligns precisely with solstices and lunar cycles. Its massive stones, some weighing 25 tons, are shaped and positioned with care that suggest knowledge of geometry and astronomy. The temples of Göbekli Tepe in Turkey, dating to around 9600 BC, predate agriculture and settled civilization, yet display complex architectural planning, symbolic sophistication, and organizational capacity. The megalithic structures of Malta, temples built between 3600 and 2500 BC, demonstrate precise stonework, astronomical alignments, and architectural complexity that challenges assumptions about Neolithic capabilities. Across the Atlantic, the Nazca lines in Peru create enormous geometric shapes visible only from the air. Designs whose creation required mathematical planning and surveying knowledge. In Central America, pyramids and temples built by the Maya and earlier cultures display astronomical sophistication, mathematical innovation. They independently develop the concept of zero and architectural precision. A pattern emerges. Around the world, in different cultures separated by oceans and millennia, we find evidence of sophisticated knowledge, mathematical, astronomical, engineering, expressed in monumental architecture. The conventional narrative treats each of these as independent developments, evidence that human capability naturally develops along similar lines given similar challenges. But the pattern is striking, and the precision in each case exceeds what simple explanations suggest. Perhaps there's a hidden variable. Perhaps human civilization is older, more complex, more globally interconnected than our current models suggest. Perhaps knowledge spread through ancient trade routes, maritime voyages, and cultural exchanges that left only faint traces in the archaeological record. Or perhaps human consciousness, when focused and organized, is capable of extraordinary achievement even with simple tools. Because the most important tool is the mind itself, and minds in the ancient world were as capable as our own. The Great Pyramid stands as proof of this capability. It is a monument to human potential. Not just Bronze Age potential, but human potential, timeless and remarkable. In recent decades, new technologies have allowed researchers to study the Great Pyramid with unprecedented precision. Ground-penetrating radar, microgravimetry surveys and thermal imaging have revealed anomalies within the structure, possible void spaces, density variations, and internal features not visible from the outside. In 2017, an international team using cosmic ray muon detectors discovered a large void above the Grand Gallery, a previously unknown space within the pyramid's mass. The purpose of this void remains unknown, but its existence proves that the Great Pyramid still holds secrets, still has things to reveal. Laser scanning has created three-dimensional models of the structure with millimetre accuracy, allowing virtual exploration and analysis. These models confirm and extend Petrie's measurements, documenting every surface, every block, every irregularity. And what these modern tools show, repeatedly, is precision. Wherever we look, however we measure, we find accuracy that shouldn't exist, evidence of knowledge and capability that challenges our comfortable narratives. But perhaps most importantly, modern engineers and scientists are beginning to approach the Great Pyramid with humility. The dismissive certainty of earlier eras, we know how it was built and any alternative suggestions are nonsense, is giving way to honest acknowledgement. We don't fully understand. Engineers study the structure and recognize sophisticated techniques, stress distribution, foundation engineering, material selection, that demonstrate deep understanding of structural principles. Astronomers confirm that the alignments are precise and purposeful, not accidental or approximate. Mathematicians recognize that the ratios encoded in the structure are too precise to be coincidental, suggesting intentional design. This multidisciplinary approach, bringing together diverse expertise rather than siloing research within single disciplines, is producing a richer, more nuanced understanding of the Great Pyramid. And that understanding points toward a conclusion both humbling and inspiring. The ancient Egyptians were far more capable than we've acknowledged. They possessed knowledge, techniques, and organizational sophistication that equals or exceeds what many ancient cultures are credited with. The Great Pyramid is not evidence of aliens or Atlantis. It is evidence of human brilliance, ancient human brilliance expressed through stone, geometry, and vision. So what do we take from this journey into precision? What lessons does the Great Pyramid offer to us, 47 centuries after its construction? First, never underestimate human capability. The people who built the Great Pyramid had the same brains, the same potential, the same capacity for brilliance that we possess today. They lacked our accumulated knowledge, our technology, our interconnected global civilization, but they did not lack intelligence, creativity, or ambition. We are not smarter than our ancestors. We simply stand on their shoulders. Second, precision matters. The ancient Egyptians pursued perfection not because it was easy or practical, but because it was right. They built the Great Pyramid to last for ages, to embody cosmic principles, to stand as a testament to human achievement. In our modern world, we often accept good enough. We build for obsolescence, design for short lifespans, prioritize speed and cost over quality and permanence. The Great Pyramid challenges this mindset. It says, build things that matter, build them well, build them to endure. Third, mystery is acceptable. We do not have to know everything. We do not have to explain every anomaly, answer every question, resolve every controversy. The Great Pyramid remains mysterious, not because we are stupid, but because it is complex, a monument that reveals its secrets slowly, over centuries of study. There is beauty in mystery. There is wisdom in admitting uncertainty. The honest phrase, "we don't know yet," is more valuable than forced certainty that ignores evidence. Fourth, ancient wisdom deserves respect. For too long, modern civilization has dismissed ancient knowledge as primitive superstition, treating our ancestors as less sophisticated, less capable, less intelligent versions of ourselves. The Great Pyramid proves this attitude wrong. The precision in its construction, the knowledge encoded in its dimensions, the sophistication of its design, all of it demands that we approach ancient wisdom with humility and openness. Perhaps there are things they understood that we've forgotten. Perhaps there are techniques, perspectives, and insights from the ancient world that could enrich our modern understanding. Not blindly accepting ancient claims, not abandoning critical thinking, but being willing to learn, to consider that the past holds wisdom we've overlooked. Fifth, connection matters. The Great Pyramid was not built in isolation. It required organisation, cooperation, shared vision, and collective effort on a massive scale. It required thousands of people working together, generation after generation, toward a common goal. In our fragmented modern world, divided by politics, ideology, religion, and self-interest, the Great Pyramid reminds us what humans can achieve when united by shared purpose. We need such reminders. We need monuments to human cooperation, testaments to what becomes possible when we work together rather than against each other. The Great Pyramid stands. It has stood for 47 centuries. It will stand for centuries more, perhaps millennia, unless humanity actively destroys it. And as long as it stands, it will challenge us. It will force each generation to confront questions about human capability, ancient knowledge, and the mysteries of our past. New technologies will allow new measurements, new discoveries, new insights. Some questions will be answered. New questions will emerge. This is as it should be. The Great Pyramid is not just a monument to the past. It is a gateway to ongoing discovery, a focal point for human curiosity and wonder. Every person who stands before it feels something. Awe at its scale, wonder at its precision, curiosity about its purpose. These feelings are universal, transcending culture, language, and era. The pyramid speaks to something deep within us, the part that yearns to understand, to achieve, to leave something permanent and meaningful. It says, humans built this. People like you, with hands and minds and vision. They built something impossible, something that endures. And in saying this, it whispers a deeper truth. You can too. You possess the same potential, the same capability, the same spark of brilliance. Not to build pyramids, our era faces different challenges, requires different monuments. But to pursue precision in whatever we do, to value excellence, to work toward goals that transcend our individual lifespans, to create things that matter, that endure, that challenge future generations to understand and appreciate. The precision of the Great Pyramid is not just an ancient achievement. It is a living challenge, eternally relevant, forever inspiring those willing to measure, to question, to wonder. The sun sets over Giza, as it has for 47 centuries. The Great Pyramid's shadow stretches across the desert sand, its edge sharp and true, marking the passage of time with geometric precision. We have measured. We have calculated. We have traced alignments, examined surfaces, studied joints, and confronted impossibilities. And what have we learned? That precision is not just technical achievement, it is philosophy. It is the decision to care about accuracy, to pursue perfection, to refuse to accept close enough. That human capability transcends era and technology. The minds that conceived the Great Pyramid were our minds, capable of abstraction, mathematical reasoning, complex planning, and visionary thinking. That mystery is not failure, it is invitation. The questions we cannot yet answer about the Great Pyramid are not evidence of ignorance, but proof of ongoing discovery, of the inexhaustible richness of human achievement. We stand at a unique moment in history. We possess technologies that can measure the pyramid with unprecedented accuracy. Lasers, computers, satellites, scanning equipment. We can quantify every dimension, trace every alignment, document every stone. Yet despite all this measurement, despite all our modern capabilities, we remain humbled. The precision we can measure, we cannot fully explain. The achievement we can document, we cannot entirely replicate with the constraints the ancient Egyptians faced. This is not a failure of modern science. It is evidence of ancient genius. The Great Pyramid is not evidence that we need aliens or lost super civilizations to explain human achievement. It is evidence that humans, Bronze Age humans, ancient humans, our ancestors, were capable of extraordinary things. They looked at blank desert and envisioned a mountain of stone, perfectly proportioned, astronomically aligned, mathematically encoded. They planned it, organized the resources to build it, developed techniques to achieve precision, and executed their vision with exactitude that still astonishes. They did this not because they had to, but because they chose to, because they valued permanence, order, cosmic harmony, and the pursuit of perfection. What monuments are we building? What will remain of our civilization 4,000 years hence? Will future generations stand before our achievements with the same awe we feel before the Great Pyramid? Perhaps our monuments are different, not stone but digital, not physical but conceptual. Perhaps our greatest achievements lie in science, medicine, human rights, global connectivity. But there is something to be said for the tangible, the physical, the undeniable presence of stone stacked with precision. There is something profound about creating work that outlasts its creators by millennia. The Great Pyramid teaches us to think beyond our lifespans, to build for ages, to pursue excellence not for immediate reward, but for lasting legacy. It teaches us that our ancestors deserve respect, not condescension, not dismissal, but genuine appreciation for their intelligence, capability, and vision. It teaches us that knowledge can be expressed in stone as well as text, in proportions as well as prose, in alignments as well as equations. And perhaps most importantly, it teaches us to remain humble in the face of mystery, to acknowledge what we don't know, to keep questioning, measuring, and wondering. The precision of the Great Pyramid is not impossible for its age. It is proof of what was possible, what humans achieved when they combined knowledge, skill, organization, and vision. It stands as a challenge to every generation. What will you build? What precision will you pursue? What legacy will you leave? 47 centuries from now, what monuments to human capability will bear witness to our era? These are the questions the Great Pyramid whispers in its silent stone voice. These are the measurements that matter most, not arc-minutes or thousandths of inches, but the measure of our ambition, our vision, our commitment to excellence. The wind still blows across Giza. The stars still wheel overhead in their eternal patterns, and the Great Pyramid still stands, precise, enigmatic, perfect. A testament to the heights humanity can reach when we dare to build the impossible. Stand before it, if you can. Place your hand against its ancient stone. Feel the weight of history, the precision of mathematics, the vision of minds long turned to dust. And ask yourself, what precision am I pursuing in my own life? What am I building that will last? What legacy will I leave for those who come after? The Great Pyramid does not answer these questions. It simply asks them eternally in a voice of stone and shadow and starlight. And in asking, it invites us to become builders ourselves, not of monuments necessarily, but of lives lived with intention, work pursued with excellence, and visions maintained with unwavering commitment to precision. For in the end, that is the true lesson of the Great Pyramid's impossible precision. Excellence is always possible. Perfection is always worth pursuing. And human capability, properly focused and organized, can achieve wonders that echo across millennia. The measurements are complete. The journey through precision has reached its end. But the monument stands, still measuring, still challenging, still whispering its ancient secrets to anyone willing to approach with wonder and a mind open to the impossible. This is the Great Pyramid. This is human achievement. This is what we were capable of then, and what we remain capable of now, if only we dare to pursue the precision of the ages. May you build with precision, think with clarity, and create with a vision that transcends your lifetime. The past is not behind us. It is beneath our feet, supporting everything we build, reminding us of what humans can achieve when we refuse to accept the impossible.